All right, welcome back from the break. So welcome to the second session, and we will have a talk by Soonwon Choi, who will tell us about emergent universal randomness. Please take it away.
Right, thank you. Thank you everyone for coming, and thank you the organizers for giving me this opportunity to talk about my work. I'm very happy that I'm back at Berkeley, and today I'm going to talk about one of my most recent results about emergent universal randomness. So let's get started. I think to this audience, we don't have to emphasize how exciting it is to live this time. Here, I took the photos from 3 different projects or the research teams that I especially particularly admire. The one is from the Continuum. The second one is from the Harvard group. The third one is a group from Caltech. In these various platforms, we are rapidly making progress of building large-scale, sophisticated, largely programmable quantum devices. Particularly, I like those 3 papers because they represent the frontier of our technology in different directions. One is about the quality, highest gate fidelity we can achieve with reasonably many qubits. The second one, control, what is the type of operation we can do in parallel to realize even the logical qubits and their circuits. And maybe some of you might not be aware of, there's an archive paper posted from the Caltech group where they posted that they successfully created 1,200 traps and actually successfully trapped 6,000 atoms without compromising single qubit gate fidelity. That's amazing. And those systems are not just anomalously good on one directions. They also have a competitive single qubit gates and 2 qubit gate fidelities, and so on. So it's extremely promising features. Extremely promising feature is coming. As a theorist, I need to ask myself, so what should we do with those quantum devices? Maybe you might have thought about it too. Here are my answers. The first one is further improve them. We still need better and larger quantum devices. And we want to realize practical use for quantum algorithms or applications such as simulations or metrology. And using those, we want to solve some interesting open questions in science or maybe in technology. And hopefully, we explore a new regime of science that we were not able to do so in the past. And then hopefully, as always the case in our history, we discover new interesting stuff. However, even though I illustrate these 4 items, these needs not to be done in this particular order. In fact, what I'm going to present today is the last one. We will talk about what new type of physics we have discovered by playing with the analog quantum devices. And actually, using the lessons we learned from the last item, we learn how the practical techniques to improve existing quantum devices. And that's going to be the context of my talk. And the conclusion of my talk, or hopefully what I want to deliver, is a certain type of universal randomness emerges in natural quantum many-body systems. So let's get started. So I'll start by mentioning a few words about universality. What is universality? It's a big word, and maybe people have different definitions. Here's my definition. I define universality as some emergence of very important features, maybe useful features, that's independent of the microscopic details. It's a rather abstract, so let's try to be a little more concrete. Some of you might be physicists, especially the condensed matter physicists, and one of the popular concepts of universality arises at the critical point. If you have a quantum materials or just finite temperature materials and tune the system near the critical point, in many of the cases, the system exhibits diverging correlation lengths over space or correlation time, and those are diverging. And the way they diverge is a power law as a function of tuning knob, and those exponent is universal, independent of the microscopic details of how system is constituted. And this is one of the reasons that we can study this type of universal phase transitions that appears in the textbook without having to realize perfectly the same Hamiltonian in the textbook, but some other Hamiltonian in your system, because universal feature will be the same anyways, regardless of the microscopic details. There's another type of universality. It's so common, so people don't talk about. That's quantum thermalization. let's consider some initial easy to prepare quantum state and perfect isolation with the rest of the environment, and see how they evolve on the unitary dynamics and the generally chaotic Hamiltonians. After a long time, Schrödinger's equation says the system will be still pure, highly entangled quantum states. But our StemX says the system must look thermal. The resolution is, if you look subsystem A, the reduced density matrix of subsystems look like a thermal state at the appropriate temperature determined by the total energy. And the fact that this is a thermal state and the state itself is independent of microscopic details of the initial state, as long as coarse-grained measures are the same, say temperature, the particle numbers, and so on and so on. This is another type of universality we see in non-equilibrium dynamics. To this audience, our favorite dynamics is random unitary circuit. And here we also have a universality that emerges that we may not appreciate as much. Consider the product state, all zero, undergoing a particular random unitary circuit. Let's assume it's sufficiently deep, and we perform measurement of all qubits in the conventional computational basis. If you have n qubits, you have a 2 to the n different measurement outcome, each occurring with some probability. Generically, it will be exponentially small, so each probability is 1 over 2 to the n. But they'll not be exactly the same, but some of them will be a little more likely and less likely. So you will get some kind of distributions like this. If you run different instances of random unitary circuit, these probability distribution will look entirely different. So it seems like there's nothing universal, except that if you accumulate the number of B strings that falls into the particular probability distributions and put the histogram, so-called the probability of probabilities, then they look universal. For almost with the probability 1, for any deep circuit, this probability of probabilities follows near perfect, so-called the Porter-Thomas distribution, exponential distribution. This is a universal phenomena, independent of the details of the circuit. So we have a universal POPs.
May I ask, is it for Clifford or non-Clifford? Does it play a role?
It plays a role. The Clifford is fine-tuned. In that case, this does not follow the Porter-Thomas, even though the low moments will agree. Yes.
What's it bound? So if I change dimension, will be Porter-Thomas? If I change, I delete some gates, will they have the same?
The belief is if you have a computationally, universal gate set, all connected, sufficiently deep, global circuit looks like, random unitaries, forms a high-order design, and then this looks like approximate Porter-Thomas. Yes.
Just to understand the probability of probabilities, if I just sort the bit strings, then I get exactly the
same. Yeah. So you just put the histogram of the values of the probabilities, and then that's x-axis for value of probability. So it's like mean about 1 over 2 to the n, and then count. And let's take the limit that the number of qubits is very large. Everything up to some small corrections, of course. Okay, but there's something uneasy about this, which is, do we really talk about this in physics context? Why do we not see it? And also, it looks a little bit artificial because random circuit dynamics is not what we find in actual nature. In fact, I attribute that the reason we do not recognize it as a universality is actually the lack of our experimental capability. In the traditional settings, our experiment is designed so that you only look at local observables, or coarse-grained observables averaged over space or time, and also it's open. It's usually open to the environment, so the system is in a mixed state, whether in the pure state. But modern technology allows us to actually probe this physics. We can measure B-string distribution, which is non-local because it's supported everywhere. And this is microscopic observables. We can reach all resolve over space with a highly accurate time, and the system is generally isolated. So this type of new modern experiment is what enables us to probe new type of universal phenomena, maybe occurring even away from random unitary circuits. So in today's talk, it's generally 3 parts, majority the first, and briefly second, and sometime on the third, talking about 2 different kinds of universalities. They are related to one another, and then talk about how to utilize those universalities as a way to benchmark analog quantum devices. To get started, let's talk about the first projected ensemble. The projected ensemble is our way of consider the quantum state of the subsystem. In conventional system, if you have some wave function highly entangled, we look at the reduced density matrix, and often that is sufficient because you can compute any local observables from the local density matrix, especially if you are concerned about average behavior of any local density observable. But in the modern settings, we can do any other things. For example, instead of ignoring the part B, we consider performing local measurement in B and obtain some measurement outcome. Maybe the measurement outcome will be 0, 0, 0. And the part that's not measured will collapse into the wave function psi 0, 0. If you get the different measurement outcome, in general, subsystem L will collapse to a different state. Therefore, we have an ensemble of pure state that occurs with the some probability, and we can define an ensemble of pure state. And this ensemble is what we call a projected ensemble. Probably PZ, the Z enumerates different measurement outcome in B, and psi Z is a wave function on A. And this object is our object of interest, and it's more rich compared to this because it contains a correlation between the part A and B, and it contains all statistical moments because we're talking about the ensembles. In fact, the average of this ensemble is exactly rho, so it's strictly more informative than just using the density matrix. Our claim is that for a large class of quantum state, the modern quantum state obtained from natural quantum dynamics, this projected ensemble for a subsystem, sufficiently large but like reasonably small, exhibit universal distribution at the level of ensemble, not only the first moment. So you can think of it as one way of generalizing quantum thermalization. Furthermore, in the special case when the mother state is described by local effective infinite temperature, then this projected ensemble is indistinguishable up to a certain moment from the Ha random. So that's our claim. So this claim is non-trivial. So let's consider the example. Say we evolve the quantum system obtaining highly entangled quantum state that has local temperature infinity. What it means is if you look at the reduced density matrix of subsystem, it'll look like maximally mixed state because it's the infinite temperature. Here I visually pointed out as a single point in the middle of the black sphere. However, there are many different ways of considering the pure state ensemble that leads to the same reduced density matrix. So example, it would be 50-50 random up and down, or like spread all over the equators, or maybe uniformly spread over the whole sphere. All of these ensembles are distinct in terms of their statistical behavior and particularly information content. However, all of them lead to the same average behavior, which is the same reduced density matrix. This procedure of moving from density matrix to the ensemble pure state is called unraveling. And the opposite direction is just simply averaging. So the question is, what is the correct averaging? Is there any universal unraveling that occurs in the system when there's infinitely many different unraveling we could consider? Our claim is basically saying, yes, there's a universality in terms of the unraveling that happens in certain settings. So this is correct, and these are probably not correct. This is a claim, not fully proven. However, we've been collecting many examples and evidence, and I want to share with them. The first one is our rigorous results. So if you consider global state to be any typical state from the Hilbert-space, global wave function, projected ensemble generated from any subsystem is highly probable to be approximate design, epsilon approximate K designs. And we have a rigorous theorem established here. So basically, for almost all statements, our claim is true. But maybe we shouldn't be so happy because those almost all states in the Hilbert-space are non-physical states.
That's approximately the diamond concept.
Yes, it's a state design. So it's about trace distance. Yeah, state design. Yeah, sorry. Yeah. So almost all states are unphysical states. So why do we care about almost all states? In fact, we can improve the theorem to talk about reasonable low complexity state. So suppose this mother state psi is a typical state drawn from epsilon prime approximate K prime design. So for example, output of some finite polynomial depth quantum circuits. Still, the subsystem, the projected ensemble forms epsilon K design when the epsilon and K are related by epsilon prime and K prime. If you're interested in the technical details, please read this paper. So indeed, we can see that, okay, from information theoretic sense, the typical state satisfies our claim. We also have more physical examples, namely some solvable models. So here we considered 1D spin 1/2 chain dynamics. And we consider initializing the system in a particular initial state, say plus to the n, and then evolve under flow K unitaries, the time periodic dynamics that involves Ising interaction and the rotation along y. In condensed matter literature, it's called the kicked Ising model. This state, if you evolve for the t physical time step, and then measure, for example, first NA number of qubits, we can rigorously prove that in the thermodynamic limit, for any subsystem size NA that's less than or equal to T, the projected ensemble forms arbitrary K design in the thermodynamic, the global system size goes to infinity. And we can prove that. One of the ingredients are mapping these dynamics using a tensor network and then use a self-duality of this particular dynamics. This is a feature of this fine-tuned dynamics, but at least it's a very physical example. Yes?
Naively, for finite time, you have a light cone. Why thermodynamic limit matters?
Because for the entanglement growth, what you said is true, but we are demanding something stronger than that. If you have a large system, the detailed structure of the ensemble can be teleported. Therefore, the thermodynamic matters. Okay, good. There's a second solvable model. Now it's a time-independent Hamiltonian evolution. And this is in the 2D square lattice. So we consider some initial state 0, the product state, evolving under this particular Ising interaction in X basis, or the fine-tuned time tau, and then consider performing measurements of everywhere in B, and then we can rigorously prove that in the limit, the system size goes to infinity, the projected ensemble for the subsystem forms arbitrary K design. And if I formulate in this way, it looks surprising, but what's happening is this fine-tuned time, after fine-tuned time, we prepare the cluster state, and this whole circuit maps to the measurement-based quantum computations.
Like many of those results, you mentioned K designs, but what is the relation between K and like size of the system, like time of evolution, right? Because yeah.
Not fully understood. So in the solvable models, we take the thermodynamic limit. So like we strictly take K, n goes to infinity first, and then talk about finite K, finite K, arbitrary finite K. Yes. Okay, those are the solvable examples. We also have a numerical evidence. So let's consider the canonical, the non-integrable Hamiltonian that's studied in the community. And then we consider time evolution of some initial product state evolving under this particular Hamiltonian. So there's no fine-tuning involved. Evolve for the variation, the various time t, and then generate the projected ensemble from numerically generate this, and then compare its statistical moment, case moment, against the case moment of the Haar distribution. I'm going to plot this trace distance as a function of time for the different values of k. So here's the result. So this is k equal 1. So we are talking about basically reduced density matrix. As a function of time, this distance generally decays until it saturates, and different line corresponds to different total system size, global system size. As we see, when the global system size increases, these decays and then saturate to a value. And if you plot the saturation value as a function of system size, we see exponential decay in the parameter regime we studied in the numerics. This is not interesting because this basically means quantum thermalization. But let's see what happens for the larger k. Even for the higher moment, k equal 2, the trace distance of the second moment also approaches the Haar distributions, and k equals 3 and 4. All these cases, this decay until saturate, but saturation value seems to scale exponentially in the number in the total system size. It seems to be true. And these properties are beyond our conventional expectation of thermalization. Here's a visual picture of what's happening. So we generate this video. So let's consider the projected ensemble for the single qubit when everything is measured. I'm going to plot on the block sphere the ensemble of states as a function of time, and it looks like this. Initially start from up, but they evolve and become very complicated. They eventually spread basically uniformly over the block sphere. And then at this point, maybe it forms like approximate, some 2 design, 3 designs. So that's what's happening. And this phenomena has been studied not only by us, but several other groups. And then we have an increasing number of papers, coming up. And in the community, generally, it's called the deep thermalization to emphasize that this is an inner, more fine-grained structure of the thermalization beyond the reduced density matrix. So what we have done is, okay, this looks good, but what if you consider finite temperature? What's nice about thermalization is universality that also holds at the finite temperature. If you evolve a system, but the global energy is not exactly fine-tuned to be the infinite temperature, our reduced density matrix for subsystem will be not maximally mixed. It'll be actually systematically biased. That depends on the choice of the Hamiltonian. Okay? And it'll be thermal. So for the Bloch sphere, maybe single qubit, it's kind of away from the middle point. And can we still talk about universality class? In fact, it's not obvious because unlike the hard random case, we don't even know what the universal, the ensemble could be, because their mean value shouldn't be in the midpoint. It's not unitarily invariant. So can we generalize the notion of Haar ensemble to the case where the mean value is not the midpoint? And past couple of years, we've been working on this problem, and now we claim that in fact, even in such case, our projective ensemble approaches the so-called generalized Scrooge ensemble. So let's talk about Scrooge ensemble. So just like many other good works, the Scrooge ensemble has been, turns out, studied almost like 30 years ago by obvious people who studied it. And then this is basically thermally deformed version of Haar ensemble. So let's talk about what it means. Like one way to understand it is just operationally understand the meaning of this. In order to sample pure state from a Scrooge ensemble, what we should do is just sample the Haar random state and then evolve under non-unitary evolutions the square root of rho A, and we obtain the unnormalized wave function and normalize it. And then you accept the state with the norm of this unnormalized state. And if you do it infinitely more times, we accumulate the state, and those will be empirical sampling of Scrooge ensemble. So this is literally Haar random ensemble distorted by the reduced density matrix. But there's a different way of formulating the same content, which is this is the most stingy way of unraveling rho A into the pure state ensemble. So what do we mean? So let's play a game. So we have Alice and Bob, and Alice picks a random index K star, and then choose a state from this Scrooge ensemble, and hand it over to Bob, the quantum state, and ask, by performing measurements, tell me which state I picked. And what Bob does is performs optimized, I wrote POBM, I think, but it's actually the projective measurement, and then perform the optimized measurement, knowing the ensemble, try to figure out this particular label K star or K tilde. Okay, estimate for the K star. We consider repeating this experiment infinitely many times and ask asymptotic amount of information that the Bob could learn about this. And that information is called accessible information. And Scrooge ensemble is an ensemble that minimizes accessible information, the most difficult to communicate. So it's the most useless pure state ensemble in terms of classical communication. And also we can show that this is maximally difficult to compress, distinguish, or use as an information transmission, as intuitively we can think of. So in more recent paper, posted on the archive last month, we did the extensive numerical simulations showing that in fact, in the finite temperature case, our projected ensemble approaches the Scrooge ensemble. And then we verify various universal scaling. And also we quote unquote derive how this Scrooge ensemble could arise from the ergodic dynamics. So if you're interested in, please read this paper. But the bottom line, the take-home message I want to emphasize is that the nature seems to generate very stingy state that hides and scrambles information or the correlation between A and B in the most difficult way to decipher. Yes?
Given density matrix, what would be the witness to identify whether this is Scrooge ensemble?
Good point. Maybe I'll postpone the answer after talking about the second part. Any other questions? So in short, it's a sample inefficient, so it's difficult. But we can just literally compute the mutual informations. Okay, so with that, let's go to the second part, the temporal ensemble. We are going to revisit some of the ideas we introduced now. So the temporal ensemble, we talk about different ensemble of states. So we consider time evolution generated by our Hamiltonian, ergodic Hamiltonian. Usually in condensed matter literature, we consider time average quantity, so-called the diagonal ensemble, rho diagonal. It's diagonal on the energy eigenbasis. But in our approach, we are going to consider the pure state ensemble enumerated by the continuous label T, and then talk about this entire statistical properties. Our claim is that this temporal ensemble is as random as it can get, bound by conservation laws such as energy and higher moments of energy. Specifically, we show that temporal ensemble is exactly equals to so-called random phase ensemble. It's not a surprising ensemble. Random phase ensemble is defined the following way. For the given energy eigenbasis, the overlap of the energy eigenbasis is fixed. The amplitude, the absolute amplitude is fixed by the initial state, but otherwise the phase is uniformly random, IID random for every eigenstate. And we show that, in fact, the temporal ensemble and this random phase ensembles are equal to one another as long as the Hamiltonian has eigenvalue state, eigenvalues that does not have any particular resonance structure. But this shouldn't be very surprising because it basically reconfirms our intuition that over time, these phase factors becomes randomized if there's no resonance. But maybe a more useful one is this idea of statistical moment. If you now compute the statistical moment of the temporal ensemble, you can rewrite in the following way, where the first term is basically the first moment of the Haar random state ensembles multiplied by rho d to the power k. And the second one is a correction that in general exponentially small in ergodic quantum dynamics. So what it allows us to do is now, looking at this formula, we can relate the statistical moment over time with the pseudo-randomness that we are very familiar with in information theory by simply deforming this moment by rho d to the power k. So what is the implication? And this type of moment has a measurable implication. And one of them is the following. One of them is the universal fluctuations from ergodic quantum dynamics. So let's consider a quantum system. This doesn't even have to be qubit systems, some particles hopping on optical lattice system, whatever the ergodic systems. We start from some initial state, time evolved by ergodic Hamiltonian, and consider performing measurement of all the particle configurations and get the snapshot. And we enumerate this configuration by Z. And if you look at the probability distributions and the probability of probability, POP, they will not be universal because this is not a random unitary circuit. However, what we know is if you look at the probability of measuring particular outcome Z over time, we can decompose them into time-independent average components and the fluctuation over time. And the systematic component is just the overlap of the diagonal ensemble with Z. But the fluctuation is coming from temporal fluctuations. And we can show that these temporal fluctuation forms approximate Porter-Thomas distribution, universal POP. So what we show is actually the Porter-Thomas distribution that we find in random unitary also appears in the ergodic dynamics as long as we properly handle the systematic bias coming from basically row diagonal components. With that, I'm going to move to the last part of my talk, which is basically utilizing what we have just learned as a practical way to benchmark quantum devices. So before that, any questions? Okay, so usually we talk about universality class in condensed matter system and the critical point, but that's class within a particular class talking about, for example, do we talk about thermalization as a universality class? That's different types of universality, right? So I don't know, maybe we should give a name. It's just Scrooge universality. So this universality class is now well defined because it's not a phase transition. Yes.
So you just mentioned that this Porter-Thomas distribution is given when you have an ergodic dynamics,
yeah,
right, given by this.
Yeah.
And you also mentioned that when you have a random circuit, we get this sort of distribution. Is there a connection between running a random circuit and this? And if there is, what is?
Yeah, that I'm just saying that there's a connection, and that is universal statistics, which is Porter-Thomas distribution. So isn't that amazing? The one is random unitary circuit, one is ergodic dynamics. Both cases, the fluctuation of the probabilities actually displays the same fluctuations. Universalities.
Yeah, it's just strange because this doesn't look very random.
That's the point. Yeah, that's the point. So you should be very, surprised. That's what I want you to be. Yes.
How do you derive this? You were kind of divide the probabilities by the systematic probabilities and get this utility?
So we just define this by averaging this over infinite time, and you define it, and this is just dividing this guy with this guy.
And you never get any zeros.
So what happens is, this is of course like approximately true, not exactly true. What happens is this formula, the high moment over temporal ensemble equals to thermal ensemble deformed by rho d, and this rho d component takes care of it. There's a correction coming from the purity of the global diagonal ensembles, but for the ergodic dynamics, this purity we expect to decay exponentially over system size.
How do you get PZ average in the experiment? Because
it's very difficult. So experimentally measuring PZ average will be difficult. So I'm going to talk about like how to do that. Basically, the short answer is we use a simulator. Yes.
In the previous part of the talk, you mentioned like the part about projective ensembles. You mentioned like when you time evolve a state under a Hamiltonian, you said after what time it approaches like a T design. And can you comment on about that part and the relation, the relation between that part and this part?
Yeah, like short answer is we do some numerical analysis and the heuristic argument, but we don't know the sharp answer. So that's very excellent questions, but we don't know the answer. Yeah, I think it's analogous.
Ensembles generated by time you.
That's right. That's right. But so far, our rigorous results are mostly based on infinite time evolution. For finite time evolution, we have a much less control about computing anything rigorously.
Like, can you say like after what time this approaches some K design?
Numerically, we have empirically, but not analytically. But that would be very desired. I would like to know too. Okay. Yes.
For different models, do you have different convergence times? Like, can you use this to like identify the cleanest models at different temperatures?
Maybe, but yeah, I don't know. So for all models we tried, this formula works. So we
like time.
No, I don't think the rate is going to be universal. But I mean, I don't want to talk about what I don't know. Like it's a good inspiration. Like go for it and then work on it. I'll be very happy to learn from you. But I don't know the answer, unfortunately. Okay, so let's talk about benchmarking. So what's benchmarking? So in ideal world, we want to run some unitary circuit preparing some interesting quantum state, pure quantum state. In experiments, we always have an imperfection here and there, resulting in a mixed state row experiment. So if you want to verify whether the Hamiltonian or the gauge we implement is correctly done, or we want to estimate the amount of decoherence of the noise, or just carefully calibrate our experimental apparatus, what's really desired is the ability to measure the overlap between row experiment and psi. Before fixing it, we need to know how bad our system is or how good our system is. So estimating the fidelity is important. However, it's challenging because how can we efficiently measure these normal co-observables, especially when we have a limited controllability, like analog quantum devices where we cannot run random unitary circuits. Such a complex, and then without the lack of control is a bottleneck in quantum technology these days. But we are inspired by the work done by Google, namely linear cross entropy benchmark. If we had the ability to run random unitary circuits, we could run it and then we obtain these B-string distributions as we discussed before. And then they are on average 1/2 to the n, but they are fluctuating. And this looks just like a speckle pattern as in the speckle pattern of this laser pointer. Some of them are a little bright, more likely than the others. And that's coming from the random interference. However, their overall fluctuation of this intensity profile is universal value because it follows approximate polar mass distributions. So we're going to use this as a feature. If you have experiment a noisy circuit, what we are going to do is we obtain these B strings that's incoherent averaging over different speckle patterns, ending up obtaining less speckle or almost no speckle. And they have a smaller amount of fluctuations. So what we do is we use this non-universal speckle pattern as our fingerprint. This is kind of almost unique for the different quantum state, and then try to benchmark how good we generate the speckle patterns from the quantum device. And that's what we do. To compare the speckle pattern of the ideal theory and speckle pattern of the experiment, either incorrect speckle or the no speckle, we can utilize the idea called the linear cross entropy benchmark. It's essentially a fancy way of saying we just measure kind of covariance where the value of the probability is treated as a variables. So this P1 is a probability of measuring Z from experiment, and P0Z is a probability of measuring Z in the ideal, and then we just multiply and then add them up and subtract the constant components. This equation, as it is written, is difficult to measure because it seems as if you need to sample many, many times from the experiment to obtain the probability of getting a particular Z and then reconstruct histogram. But we don't have to because this expression is linear in the P1 of Z experiment. We just sample from the experiment and then get the empirical estimator for this quantity by averaging the value of P0 for Z that you obtain from the experimental sample. And we can rigorously show that under reasonable parameters that's relevant to the existing experiment, this XCB is closely related to the fidelity of the system. And most important one aspect of this is that this is a sample efficient. But as I said, this approach is problematic because A, we need to apply random unitary circuit, which is not feasible in analog devices. And also it requires long coherence time. When it's difficult to apply gates, that's extra the coherence we have. So this is challenging for analog devices. But what we do is we use our emergent randomness as a resource to address these questions. Namely, instead of using the bare Porter-Thomas, we are going to use these temporal fluctuations as a fingerprint, and then redesign our benchmarking protocols. And that's what we have done. And here's our protocol. On the experimental side, so it doesn't even have to be the qubit system. It could be any analog quantum devices, well isolated from the environment. Initialize some state of interest, and quench dynamics evolve under some ergodic Hamiltonian over time t. And at that time t, one time t, obtain many snapshots of the measurement outcomes. And that's all we have to do on the experimental side. On the theory side, what we do is we numerically simulate this desired quantum dynamics explicitly. And that's going to be computationally inefficient. Therefore, our benchmarking approach is not really good for the large-scale quantum devices, except that our next speaker, Adam Shaw, will talk about how to overcome these potential limitations. But for now, let's move on. And we just evaluate this P average of Z or the P tilde Z based on this brute force numerical computation. And then we devise a new benchmark. So here is an explicit formula. Basically, the idea is an XCB formula only using this tilde component of the probability distributions. And under reasonable assumptions, we can show that our benchmark formula approximate fidelity. And in fact, using this, we can estimate what the state preparation fidelity is, the dynamics fidelity is, or the measurement fidelity is by repeating the experiment under different various conditions. But what's nice about this is that this can be done and easy to implement for the analog devices where you don't have sophisticated control. So our approach has been already implemented in the two different experimental platforms, one in the 60-atom Ripple atom simulator, and that's going to the main topic of the next talk, I believe. And Adam is sitting there. And it has been independently implemented. Another group at Caltech for the 10 superconducting qubit systems, and actually they use our benchmarking method to calibrate the coupling strengths over their device. More importantly, this approach works for the analog devices where previously we didn't know how to benchmark their devices. That means we enable them to be compared against the state-of-the-art quantum computers. So here we numerically simulate noisy dynamics based on the most relevant noise source of different platforms, bosonic particle, fermionic particle, trapped ions, or the 2D systems. And then we see that the dotted line and dashed line agrees. That means our fidelity estimator and the true fidelity agrees very well. And this is a platform independent. So this is my last slide. So the take-home message of today's talk is the following. The first, we talked about different types of universal randomness that emerges in the projected ensemble from subsystem, or temporal ensemble of the global wave function, and talk about their applications. I hope that it was convincing they take the universal form. And another message I want to make is, it seems like our nature is very stingy, and it generates highly scrambled quantum state, even at the level of this fine-grained projected ensemble. Not just the density matrix, but even the individual pure state have a structure that's almost randomized as possible. And then now that we understand this universality coming from the ergodic dynamics, we can now leverage them as a resource to do useful applications. And finally, this is maybe not a scientific message, but more like a sociology. I wanted to emphasize that, see, even with the near-term quantum devices, there's an aspect we can learn from it. So we don't have to fulfill the step-by-step, and maybe we jump into the last step and then already explore, interesting physics. So with that, I want to introduce our collaborators. It's done in large collaboration of many theorists and experimentalists. In particular, I want to highlight the Daniel Mark. I believe he's in the audience, and he did most of the theory work, including the creative, the idea generations. And also a large portion of them was done in collaboration with the experimental group at Caltech. Not only the experimental realizations, also brainstorming about what the good way to think about the problem is at the conceptual level. That's also done together with our experimentalists. Thank you very much.
Okay, we already had quite a few questions. There's more questions.
Thank you very much for the talk. It's amazing. I want to ask a question. This Scrooge distribution, is it something we expect for high temperatures or for all temperatures? Going down to, if we go like lower temperature, will we expect some transition to into different, maybe non-universal distribution?
Yeah. Where is it? Like, this aspect. I don't know. Sorry that I don't know too much. We expect this will be true, at least for the high temperature, but the finite temperature, not infinite temperature. We believe it's true. As you lower the temperature, sometimes, especially in the higher dimensions, you have a long-range correlations. And those long-range correlations could be a problem. So in fact, if you pay attention to it, we put the generalized Scrooge ensemble, and there's a reason for it. And the reason is this. Whenever we perform measurement on the subsystem B, and there's a subsystem A, actually there's an obvious way to learn more information than naive measurement, which is measuring energy eigenbasis of the B. Because the global energy is conserved, the subsystem A and the subsystem B has anti-correlations of energy, right? So what we define as a generalized ensemble is modulo that energy conservation. So if you have an energy conservation, there's a information that you can transfer through just from the energy conservation, eliminate that, and the modulo that part seems to be universal, and then follow the scaling of the Scrooge ensemble. If you do have a long-range correlations, my guess is perhaps you also need to modulo that because this long-range correlation will mitigate information. So that's my guess.
If you go to ferromagnetic phase, say you kind of take into account that you have this ferromagnetic phase, you kind of modulo this ferromagnetic correlations, and then you distill this.
That is obviously one bit more information. You measure the polarization direction, that you at least know the average polarization, right? For the long-range interacting. Yeah, long-range kinematics. Yes.
Thanks for the nice talk. About the same page, I'm just curious about, because, for finite temperature systems, we usually characterize it using a density matrix. So what's your motivation of modeling this ensemble as each state has some probability instead of each density matrix has some probability? So it'll become like a ensemble of density matrices.
So yes, that's a good question. In some sense, we are probing the fundamental limit. The density matrix is fundamentally the absence of information from observer's point of view, but not the nature's point of view. But ensemble of pure state is the best you can do as long as you have a limited access. For example, in our case, we are assuming the B part is in measuring the local basis. That's the constraint. But up to that constraint, this is the most information you can learn about. From that point of view, I think the pure state ensemble makes more sense.
Okay, we have maybe time for one more question, if there's any. Okay, if not, let's thank Soonwon again for the very nice talk.